Well, greetings, dear friends, and welcome back to our home study YouTube videos on electronics engineering technology. This sequence of videos is to supplement the concepts learned in your college labs from your professors, but in the comfort of your own lab space at home. These training videos focus primarily on a hands-on approach where you learn important industry concepts by building your own electronic circuits on prototyping boards that we commonly call breadboards. We all learn best with our own hands. The theory presented in these videos is just enough to build a solid foundation of understanding so that you can learn how to figure out your own solutions to circuit challenges that you're going to encounter in areas of designing circuits, assembly of circuits, constructing around those circuits, analyzing those circuits, and then also troubleshooting when things don't work out as expected. Finally, you should summarize with a conclusion as to the most important points that you may have learned in each topic lesson. So today, what we're going to do is introduce you to AC topic number one, and that is troubleshooting home oscilloscope and signal generator setups. We should begin with AC waveform vocabularies. And this particular slide shows in red a sine wave on an oscilloscope screen. And the sine wave is one of a number of different waveforms that we use in AC to design and analyze concepts and new circuits and how they should be doing things for us. So one of the biggest examples would be to build an amplifier circuit. Can you build an amplifier circuit? And what's so important about an amplifier circuit? Well, if you have a car radio, do you turn up the volume? Do you lower the volume? Well, what allows you to do that is an amplifier, my friends. You watch television occasionally. Now that you're in school, maybe not quite as often, but when you do watch the news or whatever, do you raise the volume, lower the volume? Well, guess what? It's an amplifier that allows that to happen. You use a cell phone from time to time, and when you do use a cell phone, well, guess what? The antenna built into your cell phone transmits a signal at a radio frequency out of your cell phone to the nearest cell tower. How do you think that happens? There's an amplifier circuit in your cell phone that amplifies a little pipsqueak signal of your voice and electronics format into a wave that can be strong enough to be picked up by the nearest cell tower. So analyzing things with AC is critical to this next step in your learning process. So let's talk about the waveform that's in front of you. If you take a look at the waveform, notice I have two red dots. The two red dots on the screen show the beginning of a sine wave, and then the other red dot shows the end of the sine wave. So the sine wave starts at our 0 volts DC reference line. So look very carefully at the kind of tan colored box and the tan colored arrow. That's listed as the 0 volts DC reference line. And on all oscopes, it's centered horizontally. It's a horizontal line centered vertically on your oscope screen. And the red dot on the far left would be indicative of a sine wave, a waveform beginning. It's what we call its rotation. So it's going to go up from the 0 volts DC reference line, follow the yellow arrows and the red trace of the sine wave up to a positive peak. And it's much like a roller coaster, my friends. Once it reaches the peak, then the waveform, the red waveform, rotates downwards, and it comes back down until it hits the zero line. So then once it hits the zero line, it'll cross over below the 0 volts DC reference line and generate the negative portion of the waveform. So the negative portion of the waveform goes down to a negative peak at the bottom of the oscope display, and then follow the yellow arrows as the waveform comes back up. And when the waveform comes all the way back up to the 0 volts DC reference line and does this one time, this is called a cycle. So if you look at the yellow arrow, the big yellow arrow, and then look at the description in the yellow box. one cycle, and I highlighted that or bolded the word cycle. And this is one of a number of things that you should be transferring into your journal. We talked about the importance of maintaining a journal through these lessons. So you write down the definitions, you write down the new vocabulary, and you have it with you. You say, well, wait a minute, Co, all I have to do is turn on your video and watch it again. No, 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 no. That's nice that you do, but having a ready reference at your hand, flipping the pages that go specifically to AC topic number one and all the vocabulary associated with it, when you take the time to handwrite neatly, no chicken scratching, when you take time to write legibly, so legibly enough that other people can read your writing, the important vocabulary and definitions, that is called learning with your hands. That's called kinesthetic learning. So you see the words, you see the definition, you should speak the word cycle. Okay, you should say it. One cycle is the part of the waveform from a starting point, comma, through its rotation, in quotes, to a point when it begins to repeat itself. That's the definition of one cycle, and that's the part of the waveform I have between the two red dots. So the red dot on the left shows the beginning of the rotation of the waveform up to a positive peak, like a roller coaster, and then it comes, down, 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 down to the zero line, and it crosses over the zero line from the positive upper part of the waveform to the lower negative portion of the waveform until it hits a negative peak. And then from that, the waveform in red rotates back up like a roller coaster going back up. And when it hits the 0 volts reference line, that's when the waveform will begin to repeat itself. And that is the point where we end the naming of that piece of the waveform as one cycle. So the definition of one cycle is the part of the waveform from a starting point through its rotation to another point when it begins to repeat itself. Take a look at the green arrows that I have in the upper portion of the page. You're going to see a green arrow from the 0 volts reference line pointing up, and it points up to what we call the positive peak. So it's labeled in black as plus VP, which stands for positive volts peak. And it is the positive half of the sine wave cycle. You look at the other green arrow in the lower portion of your diagram, the green arrow on the right starts at the 0 volts DC reference line and points downwards to the negative peak. And so that particular value at that bottommost point of the negative half of the waveform is called negative V peak. So the negative peak is the negative half of the cycle. So we're done with the green arrows and the yellow arrows, green boxes and yellow boxes. All right, now let's take a look at the pink. Pink is pretty. So pink arrow points from the tippy top of the waveform, the positive volt peak, all the way down to the very bottom of the negative volt peak of the waveform. So it's top to bottom, and that is labeled as V double P, volts peak to peak. You never say VPP. We don't say PP to anybody. It's just kind of bad form. You say volts peak to peak. And that designates from the positive peak to the negative peak. And very simply, it is a multiple of 2. You take the V peak, you multiply by 2, and you get the volts peak to peak. Then you have something very unique in the kind of a clay-colored box. So the clay-colored box and the clay-colored arrow designate something called VRMS. And in a later lesson, we'll talk in greater detail of what VRMS represents. It does stand for root mean square, without getting into any heavy math of how that's determined. Fundamentally, what you need to know about volts root mean square, V or VRMS, is very simply that is the AC value that can be determined by measuring with a digital multimeter. The digital multimeter we've been using through all of the DC topic YouTube videos will be able to measure an AC waveform, not graphically like this oscope, but it will be able to measure the AC value. How much AC is measurable on a digital multimeter is in a form called VRMS. And to calculate is very simple. You just simply take the V peak and you multiply it by 0.707. So it's roughly 70.7% of the peak, which is represented by the bold dashed black line. We'll talk more about this when we get into measurements and why it's significant in later lessons. But right now, just want to get the introductory vocabulary in your hands. Then take a look at the blue box and the blue arrow. Very important terminology here also. Period, in black, bolded, is represented by a symbol called T, capital T, and that stands for the time for one cycle. And a time is measured in units of seconds, milliseconds, microseconds, nanoseconds, etc. We'll show you how to read information off the oscope in the next few slides, but let's just make sure you have these vocabulary elements written in your journal. So cycle is the most important definition. Period is another very critical definition. Volts peak is a graphical determination for both positive VP and negative VP. The 0 volts DC reference line will appear in every oscope trace. It's always in the middle, going left to right. VRMS is, you'll never see it as a dashed line on your oscilloscope. It is, however, a value that your digital multimeter will be able to read that is approximately 70.7% of the peak. And then finally on the far right, you have the volts peak to peak. All right, let's continue with other parts of the oscope screen. All right, so what we have here, my friends, is in the green, let's go ahead and start with the green. The green box shows major vertical division lines. So they go up and down. And I have the green arrows pointing to several of the vertical dashed lines. Those dashed lines are called vertical division lines because they help us to be able to determine measurements of the waveform as they are displayed on the oscope screen. And these are called major vertical division lines because I also have in blue minor division markers. The minor division markers, you see like little hash marks, if you will, on the 0 volts DC reference line. If you look between the major divisions, you'll see what appears to be 4 hash marks dividing that major division into 5 parts. So each minor division marker represents 1/5 of a major division, or approximately 0.2 of a major division. Knowing this terminology will help you more precisely make measurements when those waveforms don't line up with a major division line. The waveform as I have generated on this display does happen to line up with major vertical division line, as did the previous one. The waveform on the far left starts at the 0 reference line and also starts at the intersection of a vertical reference line on the far left-hand side. And it rotates up to a positive peak and goes through its rotation as we've explained before. The pink box and pink arrows describe something called major horizontal division lines. And the horizontal division lines go left to right. And I have the arrows placed on 3 of them going left to right. And they reveal something called amplitude. Amplitude is defined in yellow as signal strength. How strong is that signal? If you have a weak signal, the sine wave will probably be pretty small. If you have a strong signal, a sine wave will appear to be very, very tall. So think of amplitude defined as signal strength. And if you look very closely at the Latin root of the word amp, wow, that sounds like your car amplifier, sounds like your cell phone antenna amplifier, sounds like your television speaker amplifier. Same meaning. So amplitude is how strong that signal is, and it is measured in units of volts as we count the divisions from top to bottom. And like I say, we'll just get through the vocabulary first, and then I'll have some samples of waveforms, how to read the waveforms on these displays. Pretty straightforward, pretty simple, but you got to have this vocabulary in place first. Okay, let's take a look at the next. And the next is a review from our electronic units table, and I've kind of expanded the electronic units table with a couple of rows here. So from the electronics unit table, we do have the symbol of a quantity. The quantity is spelled out. We have units for that quantity. We have the symbol for the units. We have the description of that quantity, and then the scientists who gave this to us. So the very first row shows quantity called frequency. Frequency is what AC is all about. You'll see here in a little bit. Frequency, the symbol for frequency is a lowercase f. The units of frequency is hertz, H-E-R-T-Z, much like the car rental company. The symbol for the units is capital H, lowercase z. So hertz is the unit for frequency, and the symbol for the quantity of frequency is the lowercase f. How do we define this? How do we describe this? This is described as number of cycles per second. The number of cycles per second. So your household electricity as it comes in from your utility company is 120 volts RMS. Hear that RMS term again, but it's also delivered to your house at 60 hertz, meaning 60 cycles per second. So if we were to put our probes into the AC socket, which we won't, and I don't encourage you to do that, the oscilloscope would display within a 1 second period of time 60 sine waves. Pretty cool. And this was given to us by a German physicist by the name of Heinrich Hertz. Next line, I have frequency repeated. However, I've chosen to, in place of the brief definition, I've given you a formula because it has a reciprocal relationship with another quantity further down the electronic units table. So the formula is given as frequency is equal to 1 over capital T. And capital T, you'll see down below, is the symbol for period. We talked about period in the previous slide. Period is the time for one cycle, and it's measured in units of seconds. So frequency and period have a reciprocal relationship to each other. If you know one, you can calculate the other. If you know the other, you can calculate the one simply by inverting it. Period. Actually, the next one is time. So time is measured in units of seconds, and the symbol for time is lowercase t, and the symbol for seconds is a lowercase s. Keep in mind, it's a lowercase s. Sometimes in the literature, you may see it misprinted with a capital S. Seconds is represented only by lowercase s. The capital S, as you can see from the electronic units table, is the symbol for Siemens, which is a unit for conductance. That's on the far right of your screen. So it's a lowercase s. Below that is T for period, capital T for period, in units of seconds. Seconds also lowercase s, defined as the time for one cycle. And then finally, the last row shows period with as a formula. T, which is the time for one cycle, that is period, is equal to the reciprocal of frequency. Say that, the reciprocal of frequency. And then I reiterated the definition for one cycle with a singular sine wave on the screen, and I'll repeat the definition for the sake of redundancy. One of the most redundant instructors you'll ever encounter. Anyway, so one cycle is that part of the waveform from a starting point through its rotation to a point when it begins to repeat itself. So here's where you can be redundant. Here's what can help you learn things better. Can you memorize these terms well enough that you can explain this to your classmate when you get back in lab, next opportunity that you are in lab? Oh, Yes, I know. I can define cycle. Don't just say you know what a cycle is. Can you speak it? Can you say it out loud? Because you don't own it unless you can speak it. And truth be told, when it comes to owning versus loaning, which would you rather be? Would you rather be the owner of your own piece of property or want to be a renter? Well, most of us start off as renters, but ultimately the goal is would be nice to own your own property. Well, the same thing is true with knowledge. You're taking the time to learn this stuff now. So, all right, do you want to be the owner of that knowledge or you just want to be renting this information to pass the next test? Well, to build a solid foundation, I encourage you to own it. And the way you own it is by being able to speak it to a classmate with a sense of confidence, with a sense of conviction, and also with a sense of authority, because you are not always going to be the low man on the totem pole grunt in the company. You want to aspire to become a manager, a supervisor. How do you get there? You get there by being able to speak competently, be able to speak confidently, and also be able to speak authoritatively. How can that happen? Well, you practice in lab. You go in the lab next time, you say, I can define one cycle. And you say, one cycle is that part of the waveform from a starting point through its rotation to a point when it begins to repeat itself. So there, be confident. All right, let's go on to the next one. There we go. I want to show you waveforms, two traces in this case. And what I have is a simple voltage divider. The simple voltage divider is not set up with the DC source. I'm setting this up with a function generator. And the function generator generates different waveforms. It generates sine wave, square wave, triangular wave, different kinds of waveforms. And so what I've done is I've set this up to generate sine wave. You'll find in the literature, your textbooks, and what your professor will teach you in the theory portion of the course, all the background theory of how AC waveforms are generated, how they're propagated, how they're distributed. We're going to focus our attention not on the physics of it, but we're going to focus our attention on the hands-on side of this. What are you actually going to see from the circuit to the oscilloscope? So that being said, the waveform is called a sine wave. When we get into square waves and triangular waves, I'll describe them as well. But this is called a sine wave. And so I've got a sine wave generator. You can read from the box on the far left. I have a frequency. Frequency is given as 1 hertz. 1 hertz. And then the amplitude is a 10-volt peak. All right. So what I want to demonstrate here is really that the waveforms are said to be in phase with each other. What does that mean? That means the waveform number 1 is, if you look at the oscilloscope in green, it has a channel A and it has a channel B. The channel A has a positive lug, and the positive lug hooks up to the top of R1. So we're measuring the value of the signal as it comes out of the function generator at the top of your 2-resistor voltage divider. So that is the beginning in channel A. And channel A happens to be the waveform the higher of the two. Channel B on the oscilloscope, the green box, you can see, follow that red line down, and it goes to a node that is right in between R1 and R2. Well, this is a simple 2-resistor voltage divider. If they have identical values, well, guess what the voltage across R2 is going to be? If R1 is equal to R2, does it make sense that the voltage across R2 is going to be half of the total? 2 resistors of the same value will divide the source voltage in half. So that's represented by the lower waveform. The lower waveform is traced exactly 1/2 of the upper waveform. But what I want to show you and describe here is in phase. So what in phase means, if we read the narrative, it says in phase waveforms start at the same time, comma, rotate to the positive V peak, rotate to the negative V peak, and rotate to end at the same time. Another very important definition you should write down is one rotation of a cycle is 360 degrees. So from beginning of a cycle all the way to the end of one cycle is 360 degrees. And where this becomes significant is when we get into more advanced electronics here in the AC side of the world. We'll be talking about some differences between these waveforms that are measured in units of degrees. Okay, so in phase, that simply means both of these waveforms hit a positive peak at the same time. Both of these waveforms reach a zero at the same time, as you can see. Both of these waveforms reach a negative volts peak at the same time. And then they come back to zero at the same time and then continue along its merry way to hit a positive peak at the same time. So when you see waveforms that peak positively at the same time and peak negatively at the same time and also cross over to zero at the same time, what is the phase relationship of these waveforms? Did you hear the question? What is the phase relationship of these waveforms? The phase relationship is that they are, in quotes, in phase waveforms. They are in phase with each other. Okay, let's take a look at something that contrasts this. Here I happen to have an op-amp amplifier circuit. You'll see this in a later lesson. And what's interesting here is I have my function generator, my XFG1. That's the model of the function generator in the SIM program. And I have its positive output attached to the left side of C1, capacitor number 1. The signal will flow in two directions. The AC signal will be read by channel A of the oscope. So if you look at channel A of the oscope, the green box above it, channel A has a red wire that attaches to a node that is also connecting the positive output of the function generator going into the capacitor. And then the signal will go into the circuit. The ground of the function generator is attached to ground. The grounds of the oscope are attached to ground. And as I've said, this is an open loop schematic. We've explained open loop in a previous training video, open loop versus closed loop. This keeps things looking much neater than having all the grounds tied together at one point. Then, if you take a look at channel B of the oscope, channel B has a red wire that comes down and goes all the way to the right, and it goes to the top of the R load resistor, on the top of the 1K ohm resistor. So what we're measuring is a difference between the waveform going into the circuitry at C1 and then the waveform coming out of all that circuitry at C2 going into the load of 1K ohm load. So input of the amplifier to the output of the amplifier. So this is a true amplifier circuit. You'll be building these in labs if you haven't already done so, but we'll be doing this as a lesson down the road. Take a look at my function generator box on the far left. Function generator box says sine wave, says 1 kilohertz, amplitude 3 volt peak. And then if you take a look at the waveform, are these in phase or what? Well, they're clearly not in phase. They're not hitting positive peaks at the same time. They're not hitting negative peaks at the same time. What's going on here? So if you read the title of the page, it says phase inverted waveforms. These are inverted, meaning they're opposite of each other. So phase inverted waveforms start 180 degrees apart. What does that mean, 180 degrees? You remember one cycle is 360 degrees. Well, what that means for 180 degrees is this. When one waveform starts at zero and it rotates up to a positive V peak, so such as the smaller waveform on the trace of the oscope display, the smaller waveform starts at the 0 volts reference line. It rotates upwards until it hits a positive volt peak. When it does that, the other waveform, the larger waveform in this particular case, also starts at 0, and it rotates to a negative volt peak. So they're volts peaking at the same time, but they're volts peaking in opposite directions. When one waveform is peaking positive, the other waveform is peaking negative. Interestingly enough, both waveforms rotate to 0 volts at the same time. Notice how the waveforms intersect, how they cross each other, and they cross each other beautifully at the 0 volts reference line. So here's a question for you. You write down the question. The question is, as I've said in the previous slide, what is the phase relationship of these waveforms on this oscilloscope display? What is the phase relationship? You simply say these are phase inverted, or they are 180 degrees out of phase. That's another way of saying this. Write this down. They are 180 degrees out of phase, very specifically. They can be, waveforms can be any number of degrees out of phase, but phase inverted, being completely opposite of each other, they are exactly 180 degrees out of phase with each other. Okay, another phase relationship. Take a look at the next one. These are called out of phase waveforms. And the circuit's a true circuit. It happens to be an RC time constant circuit, which you'll learn in further lessons coming up. That's not important. What is important is I've got a function generator attached to the same node that channel A of the oscilloscope is attached to. So channel A is reading the signal as it's coming out of the function generator, going into C1 on the left-hand side. Channel B of the oscilloscope is coming down and going to the top of R1. It is measuring the peak voltage across R1. So one channel A is in front of the capacitor, and channel B is after the capacitor. So what do I have in the function generator? The function generator is showing sine wave, 1 kilohertz, and interestingly now we have a 12-volt peak. Okay. What's interesting here is if you look at the waveforms, if I were to ask you what is the phase relationship of these two waveforms, could you say that they are in phase, yes or no? Are they in phase, yes or no? Are they both peaking positive at the same time? Are they both peaking negative at the same time? Are they both crossing 0 at the same time? The answer is no, no, and no. So they're clearly not in phase. What is the phase relationship of these waveforms? Are they phase inverted? What does that mean? Well, when one reaches a positive peak, is the other waveform reaching negative peak at the same time? Nope. So these are not 180 degrees out of phase. These are not phase inverted. So what is this third relationship? What is this called? Well, if you look at the title at the top of the slide, it says out of phase waveforms. Well, the previous one was out of phase. The previous one was exactly 180 degrees out of phase. So yes, these are phase inverted, and they are also out of phase. Out of phase by how much? 180 degrees. So it's easier just simply to call these phase inverted. However, in this particular slide, as we read the narrative, as waveform at cursor 1 in red, look at the red vertical line dropping down, look at where that cursor line, the vertical line, intersects the smaller waveform at the 0 volts DC reference line. As that waveform starts at the 0 volts DC reference line, waveform at cursor number 2, look at the blue vertical line, that's called the cursor line. It's like a ruler, if you will. And so if we have the cursor number 2 in blue, where the taller waveform begins at the 0 line, there's an actual measurement we can determine. On the oscilloscope display, you can see in the text portion, right, the bottom of near the lower left of the oscilloscope display, you'll see T2 minus T1. T2 minus T1 shows us the time between the two waveforms. And I'll get into the math with you later, but we simply read this in degrees, in seconds, actually, as time is in units of seconds. Time can also be measured in units of degrees. But in terms of seconds, this is clearly we have 77.419 microseconds. After the first waveform begins, the second waveform begins. And with a little bit of math, which I will explain later, not to worry about it for now, these waveforms are not 180 degrees out of phase. They are 27.72 degrees out of phase. We'll show you how to get there later. But for right now, just simply recognize that the waveforms are out of phase. So to answer the question, what is the phase relationship of these waveforms? You simply say the phase relationship is that they are out of phase by 27.72 degrees, or they are out of phase by 77.419 microseconds. Either terminology will describe how far they are out of phase with each other. All right, now let's get into some nitty-gritty, deeper details of oscilloscope reading. All right, so here you can see in the yellow box at the top, 5 hertz. Now remember, capital H, lowercase z is the symbol for hertz. Hertz is the unit of frequency. So 5 hertz means what? 5 cycles or 5 complete waveforms in a 1-second time frame. So what I have on the oscilloscope is a 1 second between the red dots, and I have how many complete cycles between the 2 red dots? I have 5 complete cycles. So if the 2 red dots represents a time of 1 second, and I have 5 complete waveforms between the first red dot to the last red dot, I have 5 cycles per second, otherwise known as 5 hertz, okay? And the rest of the details will be revealed a little further, how we actually do the math to determine different parts of what's going on with the waveform. Look at the blue box at the bottom. If the red dot to red dot represents 1 second, then the period of 5 hertz, what does period represent? If you go back to your journal notes, as you wrote this down in your journal, period was a new vocabulary. Flip the page, look it up. Period was the time for 1 cycle. So from red dot to red dot, if that represents 1 second, then the period of 5 hertz is equal to 1 over the frequency. The frequency of 5 hertz is 1 over 5. And so what's 1 over 5 on your calculator? You'll calculate 200 milliseconds. So the time for 1 cycle is 200 milliseconds. All right. Well, this is a sample just to whet your appetite. Now we'll get into the weeds of counting our oscilloscope values starting at 1 hertz. So we'll gradually go from 1 hertz to, I think, 5 to 10. Anyway, you'll see in a moment where we're going. So in this particular slide, we're going to get into frequency details. And as we look at the trace and we look at the information on the screen, take a look at the yellow box at the top. Start at the top. Top says we have 1 hertz. How do we know it's 1 hertz? We'll look at the function generator box on the left. The function generator box says I've selected sine wave and I've set the frequency at 1 hertz. What does that mean? That means 1 cycle in 1 second. And then the amplitude here happens to be 3-volt peak. All right. So let's take a look at the red dot to red dot. I have waveform starting at the left red dot, rotating up to a positive peak, down to the 0 line, rotating to a negative peak, and then back up to the 0 line. So 1 complete cycle fits in the time frame of 1 second between the 2 red dots. Now, 1 second is 1,000 milliseconds. If you key 1,000 milli into your calculator and hit equals, you'll see that it comes up 1. Now, we're going to analyze this 2 ways. I have in the blue box, graphically, we're going to do an analysis, and mathematically, we're going to confirm that we're reading things correctly graphically. So graphically, let's look at this. Each horizontal division represents 100 milliseconds of time. How do I know that? Well, all oscilloscopes have to display some information for you, and I have put in the oval, the red oval, around what we call time base. That is a scale that tells you what is the space between the vertical division markers. The vertical division, the major division markers are 100 milliseconds apart. Okay, that's good to know. So if each horizontal division is 100 milliseconds, that's called the time base, say time base. Time base is the amount of time in each horizontal division of the oscilloscope. One cycle is equal to how many divisions in this case? You count them up from the beginning, first red dot to the last red dot. How many do we count up? 10 of them. There's 10 divisions here. And if each division is 100 milliseconds, then 10 times 100 gives you 1,000 milliseconds. So the time for one cycle, in this case, 1,000 milliseconds, is 1 second. Now, mathematically means we're not going to look at the trace on the oscilloscope, but mathematically we'll just do this based on the function generator. If the function generator says our frequency is 1 hertz, period, I gave you the formula for. Period is defined with the letter T, represented by the letter T, and defined as the time for one cycle. So T had a very interesting relationship with frequency. We said that period was the reciprocal of frequency. So that means if you know frequency, you pop it into this formula, you can calculate the period. So since frequency is 1, 1 divided by 1 gives you 1. So the period is 1 second, or period is also 1,000 milliseconds, which is the time for one cycle. Let us continue. This shows us the 5 hertz. We kind of looked at this one way before. This is a little different way of looking at 5 hertz, but it says 5 hertz. And where do we get 5 hertz from? Well, our function generator box on the left, I have this oval. Says our frequency is, the waveform is a sine wave and the frequency is 5 hertz. Nice. So in the yellow box, 5 hertz is equal to how many cycles per second? 5 cycles in 1 second. Graphically, each horizontal division represents 100 milliseconds. That's your time base. That's the red oval, the lower left of the oscilloscope. One cycle is 2 divisions from the red dot to red dot. One cycle is from the red dot to the red dot. And one cycle is composed or comprised of 2 divisions. So if each division is 100 milliseconds, then 2 of those, what's 100 milliseconds plus another 100 milliseconds, will be 200 milliseconds. That is the time for one cycle. Mathematically, we've done this a moment earlier. If the frequency is equal to 5 hertz, as given to us by the function generator, period is equal to T, and period is the time for one cycle. So hence, we're going to use the period to frequency formula. So T is equal to 1 over F. In this case, F is equal to 5 hertz. So period, T is equal to 1 over 5. 1 over 5, you punch that in your calculator, you will get 200 milliseconds, which is the time for one cycle. The yellow arrow represents 1 second. And in 1 second, we have 5 cycles. So 5 cycles in 1 second is 5 hertz. But the period, which is far more important for us, the period is the time for one of those 5 cycles. And we can determine period graphically, and we can also determine period mathematically. All right, let us continue. And I would recommend this. If at any point in time that you feel necessary, then pause the screen and refresh your notes, reiterate what's very important that you've written down in your journals, and review each of the previous slides so that you have a confidence of how the vocabulary we've learned applies to the description that I've given you in the past couple of slides. Okay, we're going to go on. 10 hertz. So the yellow line going from yellow double-headed arrow from one end of the screen to the other represents 1 second. So 10 hertz is 10 cycles in 1 second. So you count them up from left to right. You're going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, I've got 10 full sine waves between the left side and the right side of the oscilloscope display. The frequency of 10 hertz is given to us by the function generator. And in this case, it's a sine wave and it's a 3-volt peak. Okay. Graphically, what do we need to know about this? Each horizontal division is 100 milliseconds. That's called the time base, and I have that circled, red ovaled, the lower left of the oscilloscope screen. And so 1 cycle is 1 division in this case. Red dot to red dot is 1 complete cycle, so it's 1 division. So therefore, 1 cycle is 100 milliseconds long. From the beginning of the cycle to of the waveform to the end of the waveform, 1 cycle is 100 milliseconds graphically. Now, mathematically, we're going to do the function frequency from the function generator. Frequency is given as 10 hertz per the function generator. So the formula for period is equal to t. Period is defined as the time for 1 cycle. It was that reciprocal formula we played with. And so t is equal to 1 over f. T is equal to 1 over 10. Previously, it was 1 over 1, 1 over 5. Now it's 1 over 10. Does that change the milliseconds a bit? Yes, it does. So mathematically, we're able to prove that the time for 1 cycle is also 100 milliseconds, just like what we determined graphically. Okay, let us continue. Now, 60 hertz. 60 hertz is the frequency of the 120 volts RMS coming into your homes. When we go to not now, don't take your probes and plug it into the wall outlet, please. You should only do this in the laboratory where your instructor and or lab assistant can look over your shoulder and say, what's safe to plug where? Don't do this at home. But if we were to take our oscilloscope probes and make a measurement of your AC waveform coming out of the wall outlet, it would peak at about 170 volts peak, but your digital multimeter would read something close to 120 volts RMS. Because remember, we use the oscilloscope to measure the waveform, but we use the digital multimeter to read the steady value of voltage that we commonly associate with our household electrical appliances as being 120 volts. Now, in some parts of your home, you will have 240 volts. In other parts of the industry, you may have 208 volts AC or 480 volts. All of that is delivered to us at 60 cycles per second, 60 sine waves per second, but at a much higher volt peak than what's on my display. So graphically, let's analyze this. Each horizontal division is 10 milliseconds. How do we know that? Well, the time base of our oscilloscope display has changed now. Previously, we had it set to 100 milliseconds per division. Here, in order to get a good display, I happen to have 10 milliseconds per division. Okay. And how many cycles are there that actually cross over very nicely where the waveform intersects both the 0 volts reference line as well as one of the major vertical lines. And it turns out the red dot on the far right is one of those intersection points. It's great. It happens to intersect the waveform at 0 volts reference line, where the value of the volts waveform is also 0, meaning it's the crossover between the positive half cycle to the negative half cycle. And they happen to intersect horizontal, the 0 volts reference line, as well as the vertical major division line. And so this gives you a good opportunity to count the number of cycles between those divisions. And it turns out if you count the divisions, we have 5 divisions. 1, 2, 3, 4, 5. Each one is 10 milliseconds wide. So 10 milliseconds gives you 50 milliseconds between the red dots. However, the 50 milliseconds between the red dots is for 3 cycles. Can you determine graphically the time for 1 cycle? Yeah, you've guessed it. If 3 cycles is 50 milliseconds, why don't we just divide the 50 by 3? That way you'll find the time for 1 cycle. Seems pretty straightforward, I hope. So looking at the blue box, graphically, each horizontal division represents 10 milliseconds. That's the time basis given in the red oval. 3 cycles takes up 5 divisions of your screen from red dot to red dot. 3 cycles calculates to be 50 milliseconds wide. Well, that's for 3 cycles. We are interested in the time for 1 cycle. So what do? 1 cycle would be, as you've already surmised, the 50 milliseconds divided by 3. And so graphically, we determine that 1 cycle is 16.667 milliseconds. Okay. Now, mathematically, because if we do things right, between graphically and mathematically, both end up at exactly the same value. Let's see if that's true. Mathematically, if the frequency is equal to 60 hertz, as given by my function generator on the left, 60 hertz for the frequency, and since period is equal to the letter T and period represents the time for 1 cycle, then the last line in the blue box reads period, which is T, is equal to the reciprocal of frequency. So instead of the 1 over 1, 1 over 5, 1 over 10, we now have 1 over 60. Interesting, because that 60 is the frequency. So if you go to do that, guess what? You're going to end up with, on your calculator, 16.67 milliseconds, just like what we did graphically. So things are jiving pretty good right now between your graphical analysis and your mathematical analysis. Let's go to the next one. All right. We're now into 1,000 hertz or 1 kilohertz. And here we're looking at amplitude. So previously we were looking at frequency details. Now we're going to look at amplitude details, how to read the peaks. And amplitude, to reiterate, as I've put at the bottom of the slide, is signal strength. How big is this signal? How tall is this signal? Well, from the function generator, I have this listed as 2.5 volt peak at 1,000 hertz. All right, 1,000 hertz is 1 kilohertz. Well, if we're looking at amplitude, we're looking at how big the waveform is. So now instead of time base, we're more interested in channel A, because channel A shows you the amplitude measured in a scale of volts per division. Channel B is not hooked up right now, so there's only one trace, and it doesn't matter where it's set. But this is set at 1 volt per division. Well, if you look at this very carefully, graphically in the blue box, it says per channel A scale of 1 volt per division, each vertical division represents 1 volt. So you count 1 division for this up to here, 1 division to the next dotted line. Well, where's my V peak? It looks like it's like half of the division, half of a division. Is it reasonable to call this green arrow 2.5 divisions tall? As I've indicated in green on the oscilloscope display, 2.5 divisions to the positive volt peak. And if the scale is at 1 volt for each division, then doesn't it seem reasonable that our volts peak can calculate to be 2.5 times 1 volt for each division, 2.5 volt peak in green. Look at the blue box. The blue box says the channel A scale for the vertical division is 1 volt. That's given. So the positive V peak is 2.5 divisions tall. So the positive V peak of 2.5 divisions times 1 volt for each division, graphically, we're able to determine the V peak as 2.5 volts peak. Nice. Now let's take a look at another example. Can't have enough examples. Here we go. Amplitude. I have a different amplitude now. According to my function generator, I have a different frequency, 8 kilohertz or 8,000 hertz. And my function generator says I've got 200 millivolt peak. So it's a little tiny pipsqueak signal. So we're going to probably need to magnify the signal in order to be able to read it on the display. And so where previously channel A was originally 5 volts per division, and we recently made it 1 volt per division, now we can change our channel A scale to 100 millivolts per division. What this allows us to do is to better see the rise and the fall of the waveform. So let's take a look at the green. The green arrow starts at the 0 volts DC reference line and goes up to the positive peak. How many divisions does it take for us to get there? 2 whole divisions. 2 whole divisions to the positive V peak. Then it says, well, if each division represents 100 millivolts, where do we get 100 millivolts from? Take a look at my channel A scale. I'm at 100 millivolts for each division. So 2 times 100 millivolts for each division calculates a positive V peak of 200 millivolts peak. 200 millivolts peak. Nice. Then in the tan box, you can see I've got a tan arrow from the 0 volts DC reference line to this imaginary dotted line, dash line. You won't see this dash line on the oscilloscope, but it is called VRMS or volts RMS. And this is the AC value. It's an AC value. This is the AC value that your digital multimeter will spit out. Your digital multimeter doesn't provide any graphic representation. Your digital multimeter does not provide an interpretation of the graphical measurement. It simply gives you the RMS value. And mathematically, we said it was approximately 0.707 of the V peak, which in this case calculates to be 141.4 milliVRMS. How do we find that out? Take 0.707 times 200 millivolt peak. And that will calculate to be the 141.4 millivolts RMS. And it's important, you have to write down V with the RMS behind it. Doesn't matter to really that's a lowercase RMS or a capitalized RMS. It is a subscript. So if you're going to use lowercase, it's considered a subscript. If you use uppercase, then it should be written as a subscript. All right. This is amplitude. This is how strong the signal is. And this is one sample waveform that shows you how you read the amplitude. Now, redundancy. Did I show anything else? Let's see, one amplitude. Okay, so we had amplitude details. Yeah, we had a 2.5 volt peak. And then we went to 200 millivolt peak. All right, now you're ready for a test question. Ha! You thought this was just a watch and see? No. Here's the test question. Freeze the frame, put it on pause, and write these values down that you're going to need to determine graphically from the display. You were asked to determine positive V peak, fill in the blank. You were asked to determine volts peak to peak, fill in the blank. You were asked to calculate VRMS, fill in the blank. You were asked to calculate period as the symbol T in units of seconds or milliseconds or microseconds, some value, some quantity of seconds. Then you're given the formula, frequency. Frequency is equal to the reciprocal of period, 1 over T. So once you calculate T, you can calculate frequency. So you have what? 1, 2, 3, 4, 5 things to fill in. And as you have the screen on pause, if you can't quite figure this out, go back to review the 2 previous sets of slides. Actually, the previous, two previous slides to see if you can determine from rereading how to determine the positive V peak. So write these values down in your journal, and we will review this in a moment when we come back after your pause. Okay, you got to figure it out or got some kind of numbers down? Attempt it, okay? All right. Now that you've been good students and you actually paused this and actually calculated some of these numbers and actually written them down, committed in your journal, without going immediately to the answer slide coming up, let's see how you did. All right, here's our solutions for your test answers to question number one. So take a look at the positive volt peak. How many divisions to reach the top? You have 3 divisions. What's my scale? My channel A scale is 100 millivolts for each division right here. So mathematically, it should be 3 divisions times 100 millivolts for each division. So your positive V peak should be calculated as 300 millivolts peak. Good job. Hopefully you got that. If not, this is the solution. This is how to get there. And what is the volts peak to peak? Well, we said much earlier that the peak to peak is simply the doubling of the positive volt peak. So if the positive volt peak is 300 millivolt peak, then double that will give you your volts peak to peak, 600 millivolts peak to peak. The next question is your VRMS, and the VRMS is what your digital multimeter will be able to display. Digital multimeter doesn't show you the waveform, and the digital multimeter, excuse me, the oscilloscope does not read the RMS value. That dashed line that we see is simply a hint at where VRMS, the portion of VRMS, ought to be from the V peak. So we calculate that, as I've said earlier, that is simply a 0.707, roughly 70.7% of the peak, which in this case, if you do the calculation, should work out to be 212.1 millivolts RMS. And it's very important after each of these answers to write the appropriate terminology. Volts peak, positive volts peak is milli V with a lowercase p. Volts peak to peak is with 2 P's. Volts RMS is actually written VRMS. Okay, next thing you need to determine is how to count your frequency and how to count your time for one cycle. All right, so what you look for is if you find the very first cycle, if you put the red dot here and you put the red dot here, this is not a convenient place for us to guesstimate how many divisions left to right up to this point. You can do a guesstimate, but it's always better if you can find some part of these waveforms that actually crosses the 0 volts reference line at an intersection with a vertical line. And it turns out in my display, we happen to have that spot, that intersection at the second red dot. So between the 2 red dots, I have how many cycles? It says 5 cycles. Excuse me, 3 cycles. I have 3 complete cycles, 3 complete waveforms. But those 3 cycles take up how many divisions left to right? 1, 2, 3, 4, 5 divisions. So 3 cycles takes 5 divisions. Then how many divisions is 1 cycle? Well, 1 cycle would be 5 over 3. In other words, 1 2/3 of a division would be 1 cycle. Well, how do we determine 1 cycle in terms of time? That would be determined this way. Time is given by your time base, 50 microseconds right here. And so you have 1 cycle would be 5 divided by 3, close parentheses, and then multiply by 50 micro, and you determine the period, the time for 1 cycle from here to here, that's 1 cycle, is 1/3 of the 50 microseconds. More than 1/3. Yeah, it's 1/3 of the 50 microseconds. 50 microseconds per division. So we have 1, 2, 3, 4, 5, 1/3 of 250 microseconds. Okay, because between the 2 red dots, if I have 5 divisions, each division is worth 50 microseconds. So I have 50, 100, 150, 200, 250 is the time between the two red dots. And that's for 3 cycles. I could divide 250 by 3, and I will get 83.333 microseconds. Or I can also do this mathematically, 5 divided by 3 in parentheses times 50 micro, I will still get 83.33 microseconds. Now, it's critical, absolutely critical, if we're dealing with millis and we're dealing with micros, that you key this into your calculators correctly, okay? Very important, because if you don't do the keying in of the engineering prefixes, then your answer is not going to be correct. If you try to do this without the micro, you will not end up with 12 kilohertz, okay? You'll end up with something else. So in order to do this correctly, as you look at the time base is 50 microseconds. And then you multiply that by the value of 5 divided by 3 in parentheses. And then this answer on your display of the calculator will show as 83.33 microseconds. Now, if you then reciprocate that value, you will have 12 kilohertz, okay? And that is given, if you take a look at my function generator, lo and behold, my frequency was set at 12 kilohertz and my amplitude was set at 300 millivolts peak. So in the test questioning, you were not shown the function generator. In the test question, looky here, test question number 1, you were just shown the waveform. You were shown the scale for the time base and the scale for the channel A voltage. That's all you were shown. You had to figure it out yourself, all the things that need to be looked at in order to fill in these values, okay? So yes, you are not given the function generator as any part of this image. However, in the answer sheet, the function generator does show the settings that do match the calculations that you've made. So hopefully you've copied down these answers into your journal. You have the questions, you have the answers. And let me just take a moment and review with you why it's important to key in your engineering prefixes. Okay, I've switched to camera mode and I'm using the older version of the calculator I've recommended for you. I'm going to prefer to use the older version only because the silver surface and the buttons are a little more clear. So we'll go, that's a prefix calculator here as well. This is just an earlier version of this. You just can't get that particular model anymore. But the buttons are identical in terms of what they do. So if you recall from the answers you have written down in your journal, that the amplitude, let me go to that particular slide. Hold on. Right, okay. So what we needed to do was to do a calculation of the period. So we had one cycle was 5/3 divisions. In other words, three cycles gave us 5 divisions. So if I do this for just a moment, you should have this information written in your journal, but let's just reiterate this for just one moment. All right, so as we look at this, red dot to red dot is how many divisions? 5 divisions. How many cycles here? There's 3 cycles. We're interested in one of those cycles. So how do we determine this? One cycle is 3/5 divisions. I keep saying it backwards. This instructor is dyslexic. I'm sorry. One cycle, I apologize. One cycle is 5/3 divisions, okay? And once we have the space, how wide one cycle is in terms of divisions, then we can multiply that width of one cycle, that space for one cycle, as 3, I said it backwards again, as 5 divided by 3, then multiplied by 50 micro. All right, so let's show you what that looks like on your calculator. All right, on your calculator, go back to camera mode. machine is on. So what we're going to do is we're going to do in parentheses 5 divided by 3, okay, close parentheses, and then multiply this by 50. Now it's just not multiplied by 50, it's 50 microseconds. And the way you key micro into the calculator is shift, and the micro is right above the 4, so you can see 50 micro on the display prominently. If you don't key in the micro, then the answer is going to be incorrect. So we touch this, and guess what? This shows you the 83.3333. And look at my units at the top. It does clearly show you micro. All right. So it's nice to have the prefix calculator doing this for us. But more importantly, is when we're ready to change this period into frequency, we hit the reciprocal function. It wasn't the reciprocal function, the x negative 1 key right there. So if I hit the x negative 1, I'm going to reciprocate this. And if everything goes well, I should see 12 kilohertz. 12 kilo. All right. So very important, you key in the engineering notation. So if I go to a non-prefix calculator, so here's a non-prefix calculator. This is important enough. I really want to take a moment to do this with you. So it was open parentheses, 5 divided by 3, close parentheses. So that's what we have up there, 5 divided by 3 in parentheses. Then we're going to multiply this by, and this is 50 micro. And the way we key this in on a non-prefix calculator is pretty easy also. There's your 50, and we key in micro as a 10 power, change sign, because we want a negative. We don't do this one. This one's subtract. This is a negative. So we hit the change sign button, which shows up here as 10 negative, and micro is -6. And if you don't remember your micros versus millis versus picos, then you definitely want to go back to this card, this information that I presented in a previous training video that summarizes your engineering prefixes, what powers of 10, properties, units, and then you remember that the flip side of the card shows you your resistor color coding and your ohms Watt's law formulas. Anyway, you've seen this in a previous video. So bottom line is you should have a sense that when you see 10 negative, and micro would be -6. Now we have micro. So 5 divided by 3 in parentheses times 50, 10 power -6 is your 50 micro. You hit equals. When you hit equals, you'll get some scientific notation, which is useless. You really need this in engineering notation. So you happen to have an ENG key. We're going to hit engineering. Lo and behold, there's your 83.33. 83.33, 10 power -6. Oh, 83.33, 10 power -6. It stands for micro, and then if we reciprocate this, then we end up, again, with scientific notation that doesn't help us. We hit engineering button, and guess what? It works out to be 12 kilo. Well, 10 power +3. Go back here, 10 power +3 is kilo. But with the prefix calculator, it does show you the letter K for kilo. So without the prefix calculator, you would do it this way. Now, let me show you what a lot of students do as a mistake. What a lot of students do is they take the 5 divided by 3. You could do this without parentheses. You just have to hit equals. So that's your fraction. And then you're going to multiply this by 50 micro. What a lot of students do is they multiply by 50. 5 divided by 3 equals, and then they multiply this by 50. And if they forget to key in the microseconds, they just want to key in the number, hit enter, and then hit engineering, you'd be writing down the wrong units for period. And then if you reciprocate this, let's see if we get 12 kilo. No way, sorry, Charlie, ain't gonna happen. That is not 12 kilo, my friends. Nowhere close to it, okay? So very important you do this correctly. So 5 could be divided by 3, enter. That's all right. Then we're going to multiply this by 50, 10 power, -6, enter, hit engineering. There's your 83.33 micro 10 -6. And then now if I hit the reciprocal and hit equals, 10 power 4 is no use. We hit engineering key. We have 12, 10 power 3. There's your 12 kilo. So it's very, very important you do take the time to key in the engineering quantities as they are presented to you in our lessons, okay? So just multiply the digits. You got to be sure you multiply the powers of 10. All right, that was answer to test question number 1. You think you're done? Dream on, pals. Here we go. All right. Test question number 2. Yeah, you knew another one was coming up. All right. So here you get to noodle this one out again. You have a waveform. You have the scale markings for time base. You have the channel A, volts per division. You have the questions that you need to fill in. You have the waveform as it's traced. And what can you figure out? So you need to figure out a positive volt peak, volts peak to peak, VRMS period, frequency, reciprocating the period, and what is frequency in units of hertz. So you have 5 fill-ins. You're going to need to do a bit more than 5 calculations to get those fill-ins. Put these your video on pause. Noodle this out best as you can, and we will come back in a moment after you've written down. You've got to commit, right or wrong. You got to write down the answers you think are correct in your journal. And then when you're done, then unpause this and see where the solution takes us. So here's something that might help you out. If you look at this, my red dot does not start conveniently at the intersection of the 0 volts reference line and one of the major division lines. Too bad. You are shown that it does land on one of the minor horizontal division markers. And exactly how many is this going over to the next major division marker? Looks like 2. Looks like 3 spaces on this side. Looks like 2 spaces on this side. Take a look at the other side of the waveform. Where's my red dot? My red dot looks like it's 2 away from this this vertical division mark, 3 away from this division mark. So maybe you should count the time between this division marker and this division marker. Think about that. And we'll come back in a moment after you've paused and written down your calculations. All right, so you should have answers written in your journal. Let's see how you did, okay? We're still sharing the screen, so go over to the next slide. Here we go. Let's see how you did. All right, so amplitude, pretty straightforward. You look at the channel A scale, and it's given as 1 millivolt for each division. So 1 square is 1 millivolt. Well, how many squares up does it take to reach the peak? It looks like 1.5 squares or 1.5 divisions. Oh, so if it is 1.5 divisions tall, and each division is worth 1 millivolt, then 1.5 times 1 millivolt should give you a positive peak of 1.5 millivolt peak. It's important that you write milli in lowercase. It's important you write volts capitalized. It's important that you write peak as a subscript or lowercase, because if you don't write down all these pieces of the answer, then when you go to review your notes at a later date, they will be confusing. Volts peak to peak was simply a double of volts peak. So 1.5 millivolt peak gives you 3 millivolts peak to peak. The RMS value we have in here in the tan box is calculated as 0.707 times positive V peak, and it works out to be 1.06 millivolts RMS. That hopefully is what you calculate. Now, the cycle. This takes a bit more work because the waveform does not cross over 0 conveniently at one of the major division markers. So you're going to have to read the minor division markers. So it looks like this is 2 away from this vertical dotted line. So 1 division would be here, because this is 2 away from the next division marker. So this would be a 1. This one over here would be a 2. This one over here would be a 3. This one over here would be a 4. And lo and behold, how convenient. This lands exactly 2 spaces before the next line. So you should be able to have surmised 5 divisions for 1 cycle. 5 divisions for 1 cycle. But how much is each division worth according to the time base? Each division is 10 microseconds. So 5 divisions right here for 1 cycle is equal to 5 divisions times 10 microseconds for each division. So 1 cycle is equal to 50 microseconds. Period, which is the time for 1 cycle, is 50 microseconds. However, frequency is calculated as the reciprocal, 1 over t, 1 over 50 microseconds, and that does calculate to be 20 kilohertz. How do we know whether these answers are correct? Take a look at my function generator. Shows frequency 20 kilohertz, 20,000 is 20 kilo, and the amplitude is 1.5 millivolt peak, which was our first voltage calculation. So, hey, good job figuring this out. This is really, really nice. All right, so this lays, everything that we've done so far is important in laying out the foundation of vocabulary, terms, looking at different parts of the waveform so that you can begin to do this stuff at home. Okay, you can do this at home with a little bit of help. All right, let's take a look and see how that's done. So this is my man cave rig. These are the components that you typically have in your electronics lab at your college or university that you're using with your professors and lab assistants. And so there's going to be an oscilloscope of some sort. There's going to be a function generator of some sort, probably a benchtop power supply, which is the stack of 3 components I have on the far left, and then your station computers of some sort, and then your multimeters. And so I happen to have if you notice in here, I've got a little secondary oscope in here. You can see this little oscope in comparison to the size of a laptop or in comparison to the size of my multimeters. And we'll talk about that little oscope in a little bit. But this is typically what you should have at your university lab. Now, the critical components, the most critical components to doing the AC work is really an oscilloscope and the function generator. So what I'm using, it happens to be a 4-channel input scope. I have channel 1, channel 2, channel 3, channel 4, or some people call it channel ABCD. And so I can measure 4 simultaneous waveforms on the display and analyze them appropriately. This one happens to be a 4-channel. Most of the ones in school are either 2 or 4-channel. Then the signal generator, this is what generates the sine wave, the square wave, triangular wave, any of a number of different wave shapes. This is a dual channel output. Now this is handy for not just a single channel out, and really all you need is a minimum of 1 to come out. But if I wanted to simultaneously input a square wave and then separately but simultaneously output a sine wave, I can generate 2 different waveforms out of this at 2 different frequencies, 2 different amplitudes, completely separate and independent of each other. So this is a dual channel output signal generator. And then what I had in the previous slide was a benchtop power supply. Now what you've been using are your little breadboard power supplies, but a benchtop power supply is quite a bit more stout. There's the benchtop power supply, and you magnify the screen, you're going to see this is a triple output benchtop power supply. I've got a fixed 5 volts, and I've got a variable 0 to 25 positive, 0 to 25 negative, and this thing is built like a brick. more like a concrete cinder block. It's about the weight of a concrete cinder block. So yeah, guaranteed it's going to have quite a bit more substance than the breadboard power supply that you're using. So what's it going to take, my friends? It's unlikely it's unlikely that many of you will have thousands of dollars of benchtop equipment similar to what it is that you have at school. Probably not, unless you've got rich relatives someplace, or you just have a great part-time job and earning lots of money, and you're seriously committed to your education such that you want to buy the latest and greatest and machines. Yes, you could own this caliber of machinery, but very few students have thousands of dollars to put into their rig at home. So how can you do these labs at home? Well, I've got a solution for you. It won't cost you thousands of dollars, okay? Check this out. From previous recommendations, I recommended the Bojack kit. The Bojack kit was actually the link for this is also in the YouTube narrative, so you can link to this. This was previously recommended for the DC portion of our training videos, and so if you already have one, great. You don't have to buy another one. It has all the necessary elements that we're going to need for playing with our labs forthcoming. But what I'm showing you on the left-hand side of the screen, check this out, is a compact tablet-style tabletop oscilloscope. And it is a flat panel, very, very tidy. You'll see it in real life in a moment. It has dual channel input, so you can read both two waveforms simultaneously, which is at the very minimum. You have to have two. Having four is a luxury, but you have to have at least two. You'll see that there happen to be a lot of one-channel oscopes. There happen to be a lot of one-channel digital multimeter oscopes with a tiny, tiny screen. But what I found on from Amazon, and I have an affiliate link to this in the YouTube narrative. So what this happens to have is two-channel input, and it also has a function generator. So this little guy takes the place of these two guys, which are thousands of dollars, and rightfully so, because they do so much more, ever so much more accurately and such, but they are what they are, quite expensive. You have a function generator that's necessary to generate the waveform, and you have an oscilloscope that's necessary to read the waveform. Well, reduce that in scale and reduce that just a tad in terms of quality, accuracy. You have this piece of machinery, which is really nice. It actually does a very good job for us. And the affiliate link will take you to the same pricing for this unit as you're going to find when you regularly search for this on Amazon. But the affiliate links for both of these helps us to maintain this channel for creating more fun and interesting videos. So if you're going to acquire this, and I seriously encourage you to do so if you're serious about doing these labs at home, this is really all you need. Two-channel input as well as a signal generator. And what do I have here? There's a bonus digital multimeter thrown in. That's what those ports, the banana connectors over here are. So yes, although you can still use your nice handy dandy digital multimeter that you already own that I recommended from our very first training video, you don't have to use that because this has oscilloscope readings as well as a signal generator, as well as being able to function as a digital multimeter for all the things that you wanted to use it for. Now, there is an alternative to this. If you find that the screen is a little small. It's actually not too small. It's not those little tiny handheld 2-point-something inch screens. It's actually like about 4.3 inch. But if you want something just a tad larger that has a built-in signal generator, this would be an alternative. This one is, the last I checked on this guy came in at about $100 1939, something like that. But again, it's your career, in order to be serious about this, if you're not going to get this crazy serious with your electronics at home, then certainly at least make this level of investment. It's less than a lot of textbooks that you buy in college. Or for a little bit more, just a bit more, you can have this particular model, and I also have an affiliate link for this. This also has a built-in signal generator, little larger display, lots more buttons, because this is not the function generator is not continuously variable, and you'll see why that's nice to have in the little guy that I've presented. So let's talk a little bit about the little guy that I presented for you. And the recommended O-scope, the preferred recommendation, has these functions. There is on the screen, you have an O-scope function. So if you touch the O-scope icon on this screen, then it'll show you an O-scope display. It's dual channel. So I've got two BNC connectors, one there and one there, one for channel A, one for channel B. So two channel input. Fully selectable data that's on the screen, so I can select what data. So I can read the peak values, I can read them off the screen, or you can also have the machine just calculate it for you and put it on the screen. So this is really nice as a time saver, because you've already taken the time to analyze everything on paper. You're just using this to confirm your analysis. And it also has cursors, which is really, really nice. The cursors are your rulers. Okay, we mentioned this before. And then I happen to have vertical cursors and I have horizontal cursors. And the vertical cursors, in this case, measure the time difference between the two waveforms. And we said that in one of our previous slides, they were 27.70 something degrees apart. They were out of phase by that number of degrees. Well, the cursors help you determine that. So this has cursors also, which is really nice. And it's a compact tablet. So it has an oscilloscope function. It also happens to have signal sources, your signal generator right here. 12 different waveforms. Most of the time we're going to use sine wave, triangular wave, or square waves. These are the most popular ones, and that's what's presented to you on your first page. There's a second page and third page by clicking left or clicking right down here on the function generator. The function generator allows you up here to key in the frequency you want. You want 256, you key in 256. You want 7,849, you key in 7,849. You key this right in to this box, and that is the specific frequency. So no dials, you can just key in the exact number that you want. Very nice. Amplitude. Amplitude is adjustable from 0 all the way up to 3-volt peak. And you can do this by sliding the ball on the slider, or you can actually punch in the discrete number that you want. If you want an amplitude output that's exactly 2.2, you type in 2.2 and it'll give it to you. So here, what's nice and unique about this particular signal generator as opposed to the larger white colored one I showed you as an alternative recommendation is that this amplitude is variable. You can adjust this. That larger white colored oscilloscope with all the buttons, which was the alternative recommendation, does not have this amplitude adjustable. It is a fixed 2.5 volt peak to peak waveform, and nothing you can do about changing its amplitude. If you want to change its amplitude to your circuitry, you will have to build additional voltage divider circuitry on your breadboard to achieve any kind of variability. Here, the adjustments are built in. You can do this. And duty cycle we haven't talked about yet, wasn't relevant in the previous illustrations because I didn't show you a square wave. But duty cycle is what percentage is the positive portion of the waveform to the negative. And we've had this at 50%. In other words, the positive portion and the negative portion were exactly equal to each other in terms of time. So that's duty cycle. So it's a very easy display for you to exercise. So 12 different waveforms, variable frequency from 1 hertz to 10 million hertz. From 1 little hertz, 1 hertz, all the way up to 10 million. We got you covered. The variable amplitude is from 0.1 volts all the way to 3.0 volts. It is variable, unlike many other units, which is fixed. And the duty cycle is also variable from 1% all the way up to 99%. It's a compact packet, a tablet. And there's a bonus. The bonus is, check this out. Woohoo! Come back here. The bonus is there's a multimeter built in. So there's a multimeter mode. So you slide this main screen left or right, and then you'll see multimeter. You tap on multimeter, and boom, you've got a multimeter display that's shown in my right-hand side illustration, and you can see it's very accurate. In fact, you've got an extra digit of accuracy that the handheld doesn't, simply because it's a larger display. But it's a quality digital multimeter, and it'll do all of the functions that you want your digital multimeter to be able to do. So because the function is built in, the ports are already built in, then reduces the clutter on your desktop because you don't have to use this one unless you choose to do a separate DC measurement. If you want to make two different measurements, but simultaneously see what they read, then yes, you could engage using your handheld in addition to the multimeter that's built into this tablet. So the idea here is, since it happens to be built in as a bonus, it does reduce the clutter that's on your desktop. So wave shapes, we talked about this. This is capable of generating sine wave, square wave, sawtooth or triangle wave, half wave, full wave, I mean, all of these. And we'll be using some of them. We will not be using all of them in the training videos, but you've got more than enough to keep you busy for quite some time. So what I'm going to do right now is show you how the device actually functions to a number of different things that we've done. So I'm going to switch to camera mode. Okay, so you can see your digital multimeter as we've been using it for quite some time. And then now I'm going to shift the attention over to the device of interest and show you that as a pretty compact device, it's full of a lot of information that's quite useful to you. So what is it that we have going on here is at the top, we have our three connections. We have a channel 1 of the oscilloscope. We have the channel 2 of the oscilloscope. These are the probes that are on the bench. I'll show you in a moment. We have our connection of the signal output. That's this connection here. We have our 2 banana jacks for the digital multimeter function over here. And this over here is your USB-C charging port. This has a 400 milliamp hour battery, so it'll last a good long period of time without needing to be charged in. So the other end of the oscilloscope probes is presented to you here. So here's an example of an oscilloscope probe. The other end of an oscilloscope probe has an alligator. The alligator we will attach to a pin and attach to a point of connection on the board, like so. The other end of the oscilloscope probe is a hook. So there's a hook right there. Let me do this so you can see the hook come out. Here, see the hook come out. There it is. There's the hook, simply by squeezing this way. And what I found convenient to use is because the spring is rather strong in any of these probes, and there's a fair amount of weight to the probe itself. I like using push pins as my point markers for making connections. So I'll make the connection right there. Another thing to point out to you is that the ground wire, it swivels. So you can swivel this around as necessary. And the reason why it's nice to have this be on a swivel is because depending upon how this hook connects to your board, there's times where this ground wire may be causing some connection or board issues. Another aspect of the probe that's really handy for you to know is that it has a switch. The switch will give you a one-time function or a 10-time magnification function. So you simply slide this left and right to engage the different magnification of the probe itself. So that's the business end of the probe. The other end of the probe is called a BNC connector, and a BNC connector BNC. BNC stands for British Naval Connector, or a bayonet connector. And here's an example of the bayonet connector. All right, so this fits on, you give it a twist, and it locks in place very nicely. And so this particular guy, we'll just do this for a moment, untwist first, and then lift this up, and it comes out. There's the business end of the BNC, and there's the receptacle of the BNC, and there's two pins that have to fit into the two slots. Right there, you can see slot there at 3 o'clock and a slot there at 9 o'clock. They fit on pins, so you got to look at this very carefully when you line it up. And then it's spring loaded, so you have to push down. And while you're pushing down, you rotate this collar righty-tighty until it clicks. And once it clicks, it's nice, solidly connected there, solidly connected there. This one's just a push to make the connection. So that's the BNC, or the bayonet connection part of your probe. The part of the probe that you're going to use for your connections to the breadboard is this part here. So I'm going to have this connected to the top of the voltage divider. So instead of using the DC power supplies we've used before, I'm using the function generator of this device to output my signal onto the rails. So right here, let me show you this. Here's the oscilloscope. Let's do this. Go to home, and on the home, I can select oscilloscope. I can select tap this. Tap. There we go. Oops, too far. I've got a signal source function. I've got my settings. I've got my digital multimeter. Back to oscilloscope. I want to go to the signal source. So if I want to engage the signal source, I touch that, and then there's the display that I've shown you previously on the computer screen. I can select sine wave. I can select square wave, triangular wave just by touching. So the wave shapes are there. My frequency is here, so I can touch this for amplitude, and I could change this to 5068. I want 5068 hertz. I can get exactly 5068 hertz. Now, you can't quite see this, I'm sorry, because of the glare that's on the screen. So if I touch that and do 5068 or more than that, yeah, then the display comes up. Amplitude. Oh, after I key it in, if I do key it in, if I do want 5068, something like that, I have to hit OK. Once I hit OK, then it actually will lock on the display, and that's what I'm going to get. So I don't want that. I actually want 1000 and hit OK. So now that's at 1 kilohertz. My volts peak I can adjust on the slider like this, left and right, or I can key in the specific amount that I want. It could be two. Oops, come back here. Clear. 2. So 2.2 volts, hit OK. Now it'll lock in at 2.2. My duty cycle's at 50%, almost all the time until we get into some special square wave functions, which we won't for quite some time to come. But I'm going to shoot this back up to 3 volts. And so this is how I set things up on the signal source. So I will then go home and touch this to go to oscilloscope. And on oscilloscope, I can touch this, and I can see the display on the oscilloscope of the frequency and also of the amplitude that I want. All right, so now let's see what it is we have on the board. So on the board, what I've got is a simple voltage divider. I am using my signal source to send in a signal on the red rail. And it's coming into this orange wire, and it's going to the top of the voltage divider, and it's going to be divided across this number of 3 resistors, and then a jumper wire to point D, and then back to the return on the blue rail. So I've got 2 things connected to this input coming in. One of these connectors, this red alligator, is my signal source, my function generator part of my tablet. This probe is my channel 1. So channel 1 is connected to my signal source. So I'm verifying my signal source. My signal source is supposed to be 1 kilohertz. And this probe will determine graphically whether or not I am at 1 kilohertz. The probe will also tell me, am I at the desired amplitude of 3-volt peak or not? It'll also show me in channel 2, I've got channel 2 right here connected to the same point. So I will have two waveforms, but they are in phase with each other. So when I have it on the display, it looks like one complete waveform, but there's actually two there. Now, these are my ground connections. So each probe has a ground connection. So the probe has a black alligator going to the blue rail. The function generator has a black alligator going to the blue rail. And then, of course, this probe also has a black alligator going to ultimately ground on the blue rail. Bring this up just a little bit. You can see this just a tad more clearly on my 3 grounds. So here's the ground of this probe, here's the ground of this probe, and here's the ground of my function generator. They all have to make their way to a common ground point, which is my blue rail. This is my function generator coming in. My signal's coming in on the red alligator, and my channel 1 probe is hooked up to the same point of connection. So it's giving me a read of what my function generator is outputting. And my channel 2 is going to show me a comparison between input and output, if you will. All right, so let's go to see right now with this pin, I have it connected electrically to the same point as my input. I only see what appears to be one waveform on the display. If, however, I actually do use the voltage divider as it's intended, if I were to go move this red push pin to point B, which is between resistor 1 and resistor 2, I should have a lesser amplitude waveform, a separate waveform, but smaller, shorter, if you will, not as tall as my input. Let's see if that's going to be true. So I'm going to raise this up and I'm going to pop it in here. And lo and behold, I have two traces. One is the input, which is the taller of the two, and then the darker one is the voltage at my first test point. So it is part of the total, most of the total, because it's across the two pretty good size resistors, pretty good value resistors. And so the waveform is pretty close. Now, the question is, what is the phase relationship of these waveforms? And you say the phase relationship are that they are what? Are they in phase, out of phase, or are they inverted? They're in phase. They both peak positive at the same time. They both peak negative at the same time. And they cross over to 0 at exactly the same time. Now, when I move my probe to the other part of the voltage divider, let me see if I can try to get both in the view here. You can see the dramatic change. I'm now going to move this from point B to point C. Now we notice that we knew from previous labs, point C voltage to ground was a lower amount of voltage than point B. Point A, way up here at the top, was identical to the source, which is what we had before. Point B is less. Point C will be even smaller. So watch what happens when I move this to point C. Watch the display of the oscilloscope. Voila, right there. Isn't that cool? In phase or out of phase, or phase inverted. These are still in phase. They both cross over at 0 at the same time. They both have peaks at the same time, positive peaks and negative peaks at the same time. Pretty sweet. So this is how we demonstrate in phase and voltage division. All right. Okay, I've just switched boards. Yeah, no longer have that voltage divider. I've got what's known as the RC time constant, RC circuit. And this is what we're going to use to demonstrate some phase relationships, okay? So I've got my input and my channel 1 connection. I'm going to hook up to the red rail there. I'm going to hook up my black ground alligator to a blue rail, one of some place that's convenient. And I'm going to hook this black alligator to some point in the black rail, and I'll go, let's say, right there. And then this probe will have its black alligator, say, right there. And then I have a wave shape. Channel 1 is measuring my input from my signal source. Channel 2 is measuring from top of the resistor, and the top of the resistor is right here. If I go to connect this in here, do I see two wave shapes? I'm sorry. Let me just pull this out, show you this view. Okay, so right now my channel 2 is not connected at all. I'm only showing channel 1, which is my signal source from the tablet, and it's reading the desired frequency. Now I'm going to hook this up, the channel 2, so that it is at the top of the resistor, which is the way we had it in our slide. Pop this in here like so, and push down. Nice. Is it a smaller waveform? Yes. Is it also in phase? Is it phase inverted? What is the phase relationship? You tell me. Come on now. Come on, you can do this. These are out of phase. Okay, they are out of phase wave shapes, and how much they're out of phase we'll need to determine this by using cursors. And let me Okay, so to engage the cursors, I needed to get this little soft tip pen, which you can find at the end of some pens or at the beginning of some pens. This one happens to be a pen with a little touch screen. So it is a pen. And if I retract this, then this works on your cell phone touch screen or this touch screen. So what I'm going to do is I'm going to use this engage the other functions, and the other functions would include a cursor. So if I select cursor, I can select my horizontal cursors or vertical cursors. If I do this, there's my horizontal cursors. If I do this, come here, there's my vertical cursors. And then touch this button again, they go away. And this is where I left my cursors from before. And so what this demonstrates, my friends, is I've got one cursor on the blue waveform, the smaller waveform. I've got another cursor on the secondary waveform, and the screen tells me how far apart, the data right on the screen tells me how far apart these cursors are. What that tells me is how far apart these waveforms are in terms of time. And calculation-wise, I'll show you this in a much later video, how we interpret the amount of time that we have here into degrees out of phase. So this is roughly 88 microseconds out of phase, and that's going to be roughly in the 27, 28 degree range of being out of phase with each other. So again, don't worry about the calculations, how we do that now. That'll be part of a much later significant video specifically on out of phase waveforms. But I wanted to give you this little taste of what the machine can do as a dual trace oscilloscope, as a signal generator that actually outputs a waveform onto your breadboard that you can then measure at multiple points, as we've done. Let me back this up just a tad right here. So you can hook up to your circuitry as we have designed and as we've done, and be able to see in phase, see out of phase, as well as phase inverted. Now, I don't have a demonstration of a phase inverted signal on the oscope, only because the circuit build for the out of phase demonstration is quite extensive. We will get to that, but in a much later training video. But this clearly demonstrates the capability of you being able to see two traces, be able to see different amplitudes, be able to see the voltage information that is necessary. You're able to see the RMS voltage calculated for you. We had approximated based on the peak voltage that the RMS works out to be this value. So there at 500 millivolts per division, so roughly 1.5 volt peak. And my 1.5 volt peak, as you can see, well, you can't see here, but take my word for it. My volt peak is at 1.54. And if you multiply that by 0.707, you're going to get something very close to this displayed 1.10 volts RMS. So this works really, really well to give you this information. You can decide also in the calculation what type of information you want in the measurements, what type of information you want. And then you can also save these images to a built-in memory card so you can call up the waveforms at a later date. So I can do this and go to here, image, and I've already saved like 12 different screenshots that I can recall at a push of a button right there. This is one of the ones that I've saved. In fact, this is image number 6. So it's not the same as what you saw 3 seconds ago, but it's almost identical because this is just a fascinating wave shape to display. So we come back here, tap this guy, just tap, and then actually go out of here, and tap this, and we're back to our regular display. All right, my friends. So in conclusion, let me go back to share. So in conclusion, share. Stop share. Okay, I have to click the correct share screen. All right, so if we go back here, yes, this is what you have in your university electronics engineering lab, something very similar to this and more. But for this stage of the game, we're just getting started with AC, and getting started with AC, yeah, it's really nice to have this machinery at school. The school invested a lot of money for your education as you are investing the time, but very few of us can invest this amount of money in our own home benchtops. And you can significantly further your knowledge of the AC portion of the videos coming up by acquiring your own. Well, my friends, we have covered a lot of ground today, going over the introduction of the vocabulary of learning how to use the oscilloscope, the signal generator, and also setting up an opportunity for you to be tested on how to read waveforms in terms of frequency, in terms of time, in terms of amplitude, to be able to read frequencies as they are displayed based on what the oscilloscope parameters show us without looking at the function generator details. So quite a bit accomplished today in terms of our first lesson in AC. So before we conclude, I do want to say that there is an alternative to the oscilloscope that I've been demonstrating in the hands-on portion. I want you to draw your attention to this. The upper left shows a FNIRSI dual channel oscope. It's got it's a 3 in what we call a 3-in-1. So in other words, it's got dual channel oscilloscope function. It's got a function generator that'll generate a multitude of different waveforms, and it also happens to have a bonus digital multimeter. And so in terms of build quality, in terms of functionality, it's a great little guy, and it's probably the most budget of the ones that are on the screen, simply because of its screen size. So if you can look at a 2.8-inch screen and be happy with the result, then that is the best option for you at the best prices that are available. The links for all of these options are in the narrative of the YouTube at the end. Then next is a 3.2-inch digital multimeter oscilloscope signal generator, another 3-in-1. So it's a little larger display, and as the larger display
display goes, you're going to be paying a bit more for it to be able to show you more real estate in terms of reading your traces and reading the information that is in the major and minor divisions of your oscilloscope display. And then on the lower left is the one that I had been using in the hands-on demonstration. I'm still evaluating this unit as other units, and so we'll come to a recommendation of it or the Pico. We'll talk about the Pico in a moment, but this particular one in the lower left-hand corner, which I did show to you, has the largest of the tablet screens that is multiple function, meaning it is a dual channel oscilloscope. It has a built-in signal generator. It also happens to have a bonus multimeter, which is great. And it has a pretty good size 4.3-inch screen. And it comes in just a little bit less than the one up above the 3.2-inch screen at $139. Now, there are other oscilloscope screens that are out there that are in the 7-inch range, and then there's also full-size oscilloscopes that take up a whole lot more bench space. I've looked at these in particular because they're so compact and they take up very little desk space. Now, there is also the Pico, which I'm showing on the right-hand side of the screen, and the Picoscope. Pico's a great manufacturer, been around for a number of years, and they make all different kinds of scopes from this particular model all the way up to the scope and analyzers that are in the thousands of dollars, kid you not, many thousands of dollars. And they have a very mature software that is given to you for free from the company, no subscription costs. And it works on Windows, works on Mac, works on Linux. And so the advantage here is even smaller desktop spaces. If you look at the image, it's a tiny flat pancake size thing. And it has a USB power connection. It has dual channel inputs for your standard oscilloscope leads, and it has a BNC output for function generator. So the BNC makes it a very, very stout design for your output functions, and it takes up very little space on your desktop. So what do you do with the signal? How do you see the information? What size screen do you get with this? Well, the size screen you get with this is as you hook this up to your laptop, it will be whatever size your laptop screen is. So if you're using Microsoft Surface and the tiny one at 10 inches, then hey, you've got a 10-inch screen that is way bigger than any of these other tablet screens that I've shown you so far, right in your laptop. Now, your laptop is also capable of HDMI output, and some of you have done this, as I've done in my man cave rig. I've got 2 laptops in there with 2 extension monitors, and so how big can your oscilloscope screen be? Well, it can be as big as a size monitor you want to hook up to your laptop via an HDMI connection. And that could be any size desktop monitor all the way up to a wall-mounted television. You want a 100-inch television on the screen as being your monitor. Yes, that's pretty exciting. So that's through your laptop. So the Picoscope does have to be hooked up to a laptop first, and then from the laptop you can use the laptop screen, which is, as I said, much larger than any of these other tablet type devices. And then if you choose to, you can hook up an outboard monitor of any size that you choose, from a tabletop outboard monitor to a wall-mounted television. That way you can see the biggest display possible. And the thing about size of screen, really, there's a lot to be said about size of screen. This particular instructor is myopically challenged. I need as big a display as possible. So I'll be looking forward to testing the Picoscope software and the Picoscope device when it comes in a couple of days. And we'll run it through a variety of different tests and see if it is something that is a viable recommendation. Just from the reports that I have gotten from from the college, my colleagues in college, as well as from other sources. The Pico does seem to be a wonderful alternative to the tablet tabletop unit simply because it offers the largest screen size available. Anyway, so with that being said, if you like the hands-on approach that we've been doing in this series of videos, the DC topic videos, and from this AC topic video number one, please give a thumbs up. Really, it does. The metrics on YouTube with the thumbs up does help support the channel, and it allows me to be ever more creative in generating these training videos. Give it a subscribe. That's even more significant. So I look forward to the next time that we meet. It will be AC topic number 2, and hold on to your horses. We've got a lot more good stuff coming up. So with that, I thank you very, very much for your kind attention and have a most blessed day. Adios, amigos.